Hello everyone, we would like to present our paper, Gaussian Process Online Learning with a Sparse Data Stream, for International Conference on Intelligent Robots and Systems, i.e. IROS 2020. This work has been done by Jehyun Park in collaboration with Jongeun Choi from Machine Learning and Control Systems Laboratory at Yonsei University, Seoul, South Korea. We first introduce the motivation and background of our work, then we will explain the methods and results. Our work is motivated by Arno Solin's paper, published in NIEPS 2018, Infinite Horizon Gaussian Processes. Infinite Horizon model tackles the cubic cost in the state dimensionality and reduces the cost proportionally to the square of the state dimension per data point. Due to the efficient framework, IHGP, able to successfully implement online adaptive learning on the iPhone in real time. Let's watch a video showing how efficient IHGP is. However, the IHGP has difficulty in learning time varying hyperparameters online from the sparse data stream, i.e., an information limited situation as shown in the figure. Therefore, the objective of our paper is to develop a GP online algorithm for a given sparse data stream. We follow the formulation of the IHGP. We represent GP using a linear time varying stochastic differential equation. U of t, xi of t, y sub I, and epsilon sub I are the known control input, process noise measurement, and measurement noise respectively. F of t, B of t, and C of t are the system, noise effect, and measurement matrices, respectively. For discrete inputs, state space model translates into equation 1, where A sub k is the discrete time state transition matrix, and Q sub k is the covariance matrix of the process noise. Now we assume a case of LTA-SD without control inputs. In this case, the stationary covariance of X and the system matrices A and Q are obtained as follows. Given that P sub infinity exists and is known, then Q sub k can be computed more efficiently. In steady-state Kalman filtering, we assume equidistant observations in time as t goes to infinity. Then the filter gain converges to the stationary Kalman filter gain k. Here P is the unique solution of the following discrete time algebraic Riccati equation. Finally, we obtain the predictive mean and covariance by filter recursion. Now, we will show you how to overcome the performance reduction in sparse data stream situations. We optimize the hyperparameters using a gradient descent algorithm and log marginal likelihood. To compute the gradient of the log marginal likelihood, we need to obtain the partial derivative of P, written in red. Here we compute the P prime as the solution of the Lyapunov equation. First, we differentiate the discrete algebraic Riccati equation. Substitute them with A bar and Q bar. Then the above equation becomes the discrete Lyapunov equation that can be solved for P prime. Note that we set a lower bound on the length scale hyperparameter during the optimization process to overcome the sparse data sampling. We demonstrate the effectiveness of our approach with two examples. First example is simulated benchmark data. In order to make a sparse data stream, we randomly select 20% of data samples, marked in blue. As shown in the figures, our approach successfully produces prediction and its confidence region. In order to evaluate the average performance of our approach against IHGP, we repeatedly realize the data streams with random measurement noises 30 times under different sparse rates. For each simulated data stream, we vary the percentage of removed measurements from 0% to 60% and compared the averaged RMSE values. As shown in the figure, our approach shows generally much lower averaged RMSE values than the original IHGP for overall ranges of sparsity. Second example is estimating vehicle lateral position errors. We define the lateral position error as the distance from the road center to the vehicle perpendicularly. The exact lateral position error can be obtained directly from the simulator. but we estimate the lateral position error through vision input, assuming an actual autonomous driving situation. We use the CNN LSTM network for a deep learning model to estimate the lateral position error. In the following video, we show the simulation environment. Here, we plot the lateral error and the heading angle simultaneously. Blue rectangles in the upper figure is the trajectory of the vehicle, and lower figure shows prediction results using our approach. Our method can be applied equally for heading angles. Comparison results are shown in the figure. It doesn't seem to be a big difference in this example, and it's slightly better in the regions marked with black boxes. These figures are zoomed plot of the black boxes in the previous slide. Our approach's prediction tracks the reference prediction better than the IHGP in this region. Although the performance gain by using our approach is not significant due to a small level of the randomness in our deep neural network output, we expect that our approach is effective when it is applied to cheap sensor units with high measurement noise levels. In conclusion, we presented a GP online learning algorithm for a given sparse data stream. We obtained the exact gradient by solving the Lyapunov equation and set a lower bound on the length scale hyperparameter to overcome the sparse data sampling. Finally, we demonstrate the efficacy of our approach with 2 examples. This is the end of our presentation. Thanks for your attention.